A very good morning, students. Today we'll be dealing about the types of precipitation or the rainfall. Rain is the most common form of precipitation which takes place when condensation occurs in liquid form above the freezing point, that is above 0 degrees Celsius. For precipitation, it is necessary that moist air must ascend, cool, saturate, relative humidity 100% and then condense. Adiabatic cooling due to upward movement of air, consequent expansion of volume and cooling is by far the most important mechanism of condensation and related precipitation, including rainfall. It is apparent that constant supply of moisture and upward movement of moist air are prerequisite conditions for cloud formation and rainfall. Through this lesson, you will understand what are the types of rainfall and the global distribution of rainfall and the man-induced precipitation. Thus, precipitation and rainfall are classified on the basis of conditions and mechanisms of upward movement or lifting of the moist air. There are two main mechanisms of upward movement, for example, mechanical uplifting and the dynamic uplifting, which further falls under two subcategories: convectional uplifting and the frontal uplifting of air. The mechanical and frontal uplifting of air is also called forced uplifting. Mountain barrier, when located transverse to horizontally moving air, obstructs the wind and forces it to rise upward along the slope. This is called the orographic forced uplifting of air. The frontal uplifting of air involves pushing of the warm air upward by the colder air lying below. Convectional uplifting of the air involves radiation heating of the ground surface leading to warming of surface air and consequent expansion of the air and its ascent. The process is called convection mechanism. It is thus evident from the above discussion that there are three ways in which moist air is forced to move upward and cools according to the adiabatic rates. Radiation uplift or the convection uplift due to heating of the ground surface. The air being heated expands and rises upward in the form of convection currents. The mechanism is known as thermal convection. Second, orographic uplift, forced ascent of air over the orographic barrier because of its obstruction, and frontal uplift, forced uplift of the air associated with cyclonic activities. It may be pointed out that it is not necessary that all these factors always act independently and separately in relation to the ascent of air. Sometimes more than one factor are operative. In such situations, the form of precipitation and rainfall is determined on the basis of the most dominant factor. Thus, precipitation and rainfall are classified into the three types: convectional rainfall occurring due to thermal convection currents caused due to insulational heating of the ground surface; orographic rainfall occurring due to ascent of the air forced by mountain barrier; and cyclonic or frontal rainfall occurring due to the upward movement of the air caused by convergence of extensive air masses. Convectional rainfall. The principal motivating factor behind the ascent of warm and moist air is thermal convection caused by heating of ground surface through insulation. Two conditions are necessary to cause convectional precipitation and rainfall: abundant supply of moisture through evaporation to the air so that relative humidity becomes high; intense heating of the ground surface through incoming shortwave electromagnetic solar radiation, say the insulational heating. The mechanism of convectional rainfall may be explained in the following manner. The ground surface is intensely heated due to enormous amount of heat received through solar radiation during daytime. With the result, the air coming in contact with the warm ground surface also gets heated, becomes warm, expands and ultimately rises upward. The ascending warm and moist air cools according to dry adiabatic lapse rate, which is decrease of temperature at the rate of 10 degrees Celsius per 1000 meters. The cooling of the ascending air increases its relative humidity. The moist air becomes saturated soon. The relative humidity becomes 100%, and further ascent of the air beyond saturation level, which is supersaturation, causes condensation and cloud formation, usually the cumulonimbus clouds, and thus the rainfall starts. The air still continues to rise and in the process further cools, but at moist adiabatic lapse rate and retarded adiabatic rate, which is the decrease of temperature at the rate of 5 degrees Celsius per 1000 meters due to the addition of latent heat of condensation to the ascending air released after the condensation of the atmospheric vapor. When the air reaches such height where its temperature matches with the temperature of the surrounding air, the process of condensation is more activated and hence cumulonimbus clouds are formed, and there begins instantaneous heavy rainfall. Since the ascending moist air, convectively motivated, cools soon after rising to very little height, causes immediate saturation and condensation, the convectional rainfall occurs in the form of heavy downpour. It is also apparent from the above description that convectional rainfall is a warm weather phenomenon and is associated with lightning and cloud thunder. Convectional rainfall mainly occurs in equatorial regions of low latitudes where daily heating of the ground surface up to the noon causes convection currents. Consequently, the sky becomes overcast by 2 to 3 p.m. daily, causing pitch darkness and heavy rains, and the sky becomes clear by 4 p.m. Thus, the convectional rainfall in the equatorial region is a daily, regular feature. Convectional rainfall also occurs in the tropical, subtropical and temperate regions in the summer months and in the warmer parts of the day. The following are the characteristic features of convectional rainfall. It occurs daily in the afternoon in the equatorial regions. It is of very short duration but occurs in the form of heavy showers, heavy downpour. It occurs through thick, dark and extensive cumulonimbus clouds. It is accompanied by cloud thunder and lightning. Though much of the rainfall becomes runoff and is drained off into the form of surface runoff and overland flow to the streams, but still there is sufficient moisture in the soils to daily rainfall in the equatorial regions. Outside the equatorial regions, convective rainfall is of little significance to crop growth because most of the rainwater is drained to the streams through surface runoff, which causes severe rill and gully erosion, resulting in enormous loss of loose soils. Convective rainfall supports luxurious evergreen rainforests in the equatorial regions. Convective rainfall in the temperate regions is not in the form of heavy showers, rather it is slow and of longer duration so that most of the rainwater infiltrates into the soils. Here rain are always in summers. Convective rainfall in hot deserts is not regular but is irregular and sudden. Orographic rainfall. Orographic rainfall occurs due to ascent of air forced by mountain barriers. The mountain barriers lying across the direction of air force the moisture laden air to rise along the mountain slope, and thus lifted air mass cools according to the dry adiabatic lapse rate, which is decrease of temperature at the rate of 10 degrees Celsius per 1000 meters, which increases the relative humidity of the air. The ascending air becomes saturated after reaching certain height and the condensation begins around hygroscopic nuclei. The addition of latent heat of condensation to the air causes it to move further upward and cool at moist adiabatic lapse rate, which is decrease of temperature with the increasing height with the rate of 5 degrees Celsius per 1000 meters. Thus, ascending air continues to yield precipitation with increasing height. It is apparent that the mountain barriers produce trigger effect for moist air to ascend, cool and become unstable. The slope of the mountain facing the wind is called the windward slope or the onward slope and receives maximum precipitation, while the opposite slope is called the leeward slope or rain shadow region, because the ascending air after crossing over the mountain barrier descends along the leeward slope and thus is warmed at dry adiabatic lapse rate, which is again increase in the temperature with the decreasing height or at the rate of 10 degrees Celsius per 1000 meters. Consequently, the humidity capacity of the descending air increases, resulting into substantial decrease in the relative humidity. Secondly, the moisture present in the air is already precipitated on the windward slope and thus there is very little precipitation on the leeward slope. Most of the world precipitation occurs through orographic rainfall. The following conditions are necessary for the occurrence of the orographic rainfall. There should be mountain barrier across the wind direction so that the moist air is forced on the obstruction to move upward. If the mountain barriers are parallel to the wind direction, the air is not obstructed and no rainfall occurs. For example, Aravalli's ranges running in southwest northeast direction are parallel to the Arabian Sea branch of the southwest Indian monsoon and hence Rajasthan receives very low amount of rainfall. If mountains are very close and parallel to the sea coast, they become effective barriers because the moisture laden winds coming over the oceans are obstructed and forced to ascend and soon become saturated. For example, coast range mountains situated on the western margins of North America are parallel to the Pacific coast. Similarly, the situation is same of the Western Ghats in India, which presents ideal conditions for the orographic rainfall. The height of mountains also affects the form and amount of orographic rainfall. If the mountains are very close to the sea coast, even low height can be effective barrier and can yield sufficient rainfall because the moist air becomes saturated at very low height. On the other hand, the inland mountains should be of higher height because the air after covering long distances loses most of its moisture content. There should be sufficient amount of moisture content in the air. The windward slope, also called as a rain slope, receives maximum amount of rainfall, whereas leeward side of the mountain gets very low rainfall. For example, Mangalore, located on the western slope, which is the windward slope of the Western Ghats, receives mean annual rainfall of about 2000 millimeters, whereas Bengaluru, situated in the rain shadow region, gets only 500 millimeters of mean annual rainfall. The southern slopes of Himalayas receive mean annual rainfall of more than 2000 millimeters, whereas the northern slope receives only 50 millimeters of the mean annual rainfall. Similarly, the western slopes of the coast ranges of North America receive more than 2000 millimeters of mean annual rainfall, while the eastern slopes in the rain shadow region receive less. There is maximum rainfall near the mountain slopes and it decreases away from the foothills. For example, the cities and towns located at the southern slopes of the Himalayas receive more rainfall. For example, Shimla 1520 millimeters, Nainital receives 2000 millimeters, Darjeeling receives 3150 millimeters, whereas the places away from the Himalayan foothills receive relatively low rainfall. For example, Patna receives 1000 millimeters, Allahabad 1050 millimeters and Delhi 650 millimeters. If the mountains are of moderate height, the maximum rainfall does not occur at their tops, rather it occurs on the other side. The windward slopes of the mountains at the time of the rainfall are characterized by cumulus clouds, while the leeward slopes have stratus clouds. The amount of rainfall increases with increasing height along the windward slopes of the mountains up to a certain height, beyond which the amount of rainfall decreases with increasing height because of marked decrease in the moisture content of the air. This situation is called the inversion of rainfall. The height of the mountains beyond which the amount of rainfall decreases upward is called the maximum rainfall line, which varies spatially depending on the location of the mountain, the distance from the sea, moisture content in the air, mountain slope, seasons, etc. Maximum rainfall line is at 24,000 feet, which is 7,000 meters at the equator, and 12,000 feet, which is 3,600 meters in the Himalayas, and at 21,000 feet or 6,300 meters in Alps, and 5,400 feet during summer, at 12,000 feet during winter in the Pyrenees mountains, etc. Orographic rainfall may occur in any season. Unlike other types of rainfall, it is more widespread and of longer duration. It may be pointed out that orographic rainfall is induced not only because of lifting of the moist air, but convective and cyclonic mechanisms also help in the process of the orographic rainfall. For example, in warm regions, valleys are heated during the daytime, and hence winds are also heated and ascend along the hill slopes in the form of convection currents and yield rainfall after being saturated. Sometimes forward moving cyclones are also forced to ascend along the hill slope due to obstructions offered by mountain barriers. Cyclonic or frontal rainfall. Cyclonic or frontal rainfall occurs due to ascending of moist air and adiabatic cooling caused by convergence of two extensive air masses. The mechanism of cyclonic precipitation is of two types on the basis of two types of cyclones: temperate cyclones and the tropical cyclones. Rainfall associated with the temperate cyclones occurs when two extensive air masses of entirely different physical properties, warm and cold air masses, converge. When two contrasting air masses, cold polar air mass and warm westerly air mass coming from opposite directions converge along a line, cold front is formed. The warm wind is lifted upward along this front, whereas cold air, being heavier, settles downward. Such cyclonic fronts are created in temperate regions where cold polar winds and warm westerlies converge. The warm air lying over the cold air is cooled and gets saturated, and condensation begins around the hygroscopic nuclei. It may be pointed out that lifting of the warm air along cyclonic front is not vertical like the convective currents, rather it is oblique. Since the lifting of the warm air along the warm front of the temperate cyclone is slow and gradual, and hence the process of condensation is also slow and gradual, with the result precipitation occurs in the form of drizzles but continues for longer duration. Thus, the precipitation associated with warm front is widespread and of longer duration. On the other hand, the precipitation associated with cold fronts is always in the form of thunder showers but is of very short duration. Sometimes the precipitation occurs in the form of snowfall and hailstorms. This is because of the fact that lifting of the warm air along cold front occurs quickly as cold air pushes warm air upward with greater force. Most of the rains of the temperate regions are received through cyclones. Since the temperate cyclones consist of cells, and hence weather conditions and associated precipitation in warm front or the warm sector, cold front and the cold sector differ significantly as described. When the temperate cyclone coming from the western direction draws nearer to the observation point, wind velocity slows down considerably, air pressure decreases, and then the sun and moon are encircled by a halo, which is in fact the reflection of the thin veneers of cirrus and cirrostratus clouds in the west. Temperature suddenly increases when the cyclone comes very close to the observation point. Wind direction changes from easterly to southeasterly. The cloud cover thickens and the sky becomes overcast with dark, thick and low clouds. Warm frontal precipitation. Clouds become very thick and dark with the arrival of the warm front of the cyclone, and heavy showers begin with nimbostratus clouds. Since the warm air rises slowly along the front, and hence the precipitation is slow, gradual but of longer duration. The warm frontal precipitation largely depends on the amount of the moisture and instability of the rising warm air. If the air is full of moisture and is unstable, there is sufficient precipitation. The sky is overcast and the sun is not visible for several hours. Warm sector. The warm sector comes over the observation point after the passage of the warm front, and there is sudden change in the pre-existing weather conditions. The wind direction becomes southerly. The sky becomes cloudless and clear. There is sudden rise in the temperature and increase in the specific humidity of the air, but air pressure decreases remarkably. Though the weather becomes clear, but there may be some occasional drizzles. In all, the weather is clear and pleasant. Cold front region. Temperature registers marked decrease with the arrival of the cold front. Cold increases considerably. The cold air pushes the warm air upward, and there is change in the wind direction from the southerly to southwesterly and westerly. Sky is again covered with clouds which soon start precipitation. Cold frontal precipitation. Sky becomes overcast with cumulonimbus clouds which yield heavy showers. Since the warm air is forcibly lifted upward hurriedly, the cold frontal precipitation in the form of heavy downpour with cloud thunders and lightning, but the precipitation is of shorter duration and less widespread because the cold sector is very close. Cold sector. Weather again changes remarkably with the passage of the cold front and arrival of the cold sector. Sky becomes cloudless, hence clear. There is sharp fall in the air temperature and considerable rise in the air pressure, but decrease in specific humidity. Wind direction changes from 45 degrees to 180 degrees, and thus it becomes true westerly. After the occlusion of the cyclone, the weather conditions of the pre-cyclone period again set in. Tropical cyclonic precipitation. In tropical regions, two extensive air masses of similar physical properties converge to form the tropical cyclones, wherein lifting of the air is almost vertical and is often associated with the convection. It may be pointed out that convergence mechanism provides initial trigger effect to the movement of upward movement of the convectively unstable air, which if full of moisture becomes saturated and yields heavy showers characterized by lightning and thunder. Tropical cyclones, regionally called as typhoons, hurricanes, tornadoes, etc., yield heavy downpour in China, Japan, Southeast Asia, Bangladesh, India, United States of America, etc. Global distribution of the rainfall. There is a wide range of spatial and temporal variation in the distribution of the precipitation over the globe. For example, the equatorial region records the highest mean annual rainfall, which is more or less evenly distributed throughout the year. The tropical and the subtropical hot deserts receive the lowest mean annual rainfall. The monsoon climatic regions receive more than 80% of the mean annual rainfall during 4 wet months of the summer season, which is from June to September. The monsoon lands also record the highest rainfall in the world at Cherrapunji and Mawsynram, 1087 centimeters and 1141 centimeters respectively in India. The polar regions receive precipitation in solid form. Mean annual rainfall for the whole globe is 970 millimeters, but this mean annual distribution is highly variable and unevenly distributed. Some places receive less than 100 millimeters of mean annual rainfall. For example, tropical hot deserts like Sahara, Thar, Atacama, Kalahari, Australian desert, Sonoran desert of the North Americas, etc. While some places receive more than 10,000 millimeters of rainfall, for example, Cherrapunji and Mawsynram of India. Not only this, there is much temporal variation in the annual rainfall in particular area. For example, Bahia Felix of Chile has 325 rainy days, while Arica of the same country has only 1 rainy day per year. Iquique, located near Africa, could not receive any amount of measurable precipitation for 14 years in continuation from 1899 up until 1913. It may seem strange that one of the areas with least frequent rainfall is in the same country as one of the rainiest places in the world. If some regions have high mean annual rainfall with almost equal monthly averages, for example, the equatorial regions, while in some other regions, most annual amount of rainfall is received during a few months of the year, while most of the months either remain dry or receive little rainfall. For example, 10,870 millimeters of annual rainfall at Cherrapunji in India is received only in 159 rainy days. The equatorial regions receive rainfall throughout the year, but other areas are characterized by seasonal rainfall. For example, more than 80% of the mean annual rainfall is received during 4 wet summer monsoon months in India. On the other hand, the Mediterranean regions receive most of their annual rainfall during the winter months, while summer season remains dry. It appears that precipitation is controlled by a variety of factors, and different combinations of these factors determine the spatial and temporal variations in the distribution over the globe. So, it is desirable to discuss those important factors which control the world distribution of rainfall before attempting zonal or regional distribution of precipitation. Man-induced precipitation. Man-induced precipitation refers to artificial nucleation of the ice crystals in supercooled clouds through the introduction of dry ice, silver iodide in the form of iodine powder or in the form of smoke, finely ground salt, solid carbon dioxide, iodine compounds, etc. to augment condensation process to yield precipitation. The technique of the man-induced precipitation involves cloud seeding by the above mentioned materials. The cloud seeding comes under the program of weather modification by man for various purposes. For example, hailstorm suppression, dissipation of the fog, reduction of the velocity and force of tropical cyclones, mainly in the United States of America, suppression of lightning, augmentation of precipitation, etc., wherein the latter is the most optimistic purpose. The above mentioned materials are sent upward in the supercooled clouds by aeroplanes, explosive rockets, balloons, burners to seed smoke, etc. The cloud seeding and the intended induced precipitation is also plagued by certain problems. For example, the assessment of productiveness of the cloud seeding to stimulate rainfall is not without error. The expenditure involved in the artificial cloud seeding is very high, while the result is not so encouraging. The effectiveness of the cloud seeding has not been properly demonstrated by practical experience. The environmentalists raise objections to such anthropogenic weather modification programs, as these may interfere with the natural atmospheric and environmental processes. Rain is the most common form of precipitation and the most important one too. Today, in this lesson, we have learned about the types of rainfall and their mechanisms, followed by their global distribution, and ended it